Hi there, welcome back. In this second class about survival analysis, we will continue our discussion by entering into the details of the likelihood function. We will see that by making certain assumptions about the hazard function, the hazard rate, we can obtain different models. In particular, we will focus our attention on a very important class of models that are Cox models. And within this class, in this lesson, we will focus our attention on proportional hazard models. However, before entering into the discussion about the likelihood, I would like to tell you something about the mean. Now, consider capital T, which is the random variable representing the random time at which we observe the transition event we are interested in. For example, the default of a company. Now, its expectation, mu, can be computed in the usual way, that is to say, by taking the integral between 0 and plus infinity of t ft dt, and this comes from the fact that t, the time, cannot be a negative quantity, but by using integration by parts and noticing that ft is nothing more than minus s prime of t, that is to say the first derivative of st, and by applying Border conditions like s of 0 equal to 1 and s infinity equal to 0 that derive from the fact that s of t is 1 minus f of t, capital F of t, the CDF, the cumulative distribution function, what we can do is to express mu in terms of the survival function. That is to say, the integral between 0 and plus infinity of st dt. And that's why the survival function, it's a very important object, because it allows us to compute quite naturally the expectation of our variable capital T. Let's consider the modeling of the probability of default. But what we are going to see can be easily adapted for the loss given default. Now we have n companies, and we assume that they share the same survival function S of t, the same density small f of t, and the same hazard function lambda of t. Now we pick one company I, and we observe that company up to time ti. Given what we have said last time about censoring, at time ti we have two possibilities. One is that the company actually defaults in ti, and the second is that the company is right censored in ti. So we know that in ti the company was still active, but we don't know anything about what happened after ti. In the first case, the actual default, the contribution of company I to the likelihood function is Li, and it corresponds to the density F computed in Ti, because Ti is the actual time of default. But given the relationship between the density, the survival function, and the hazard rate, we can express Fti as Sti times lambda Ti. Just go back to last time to see how we can do that. In the second case, that is to say the case of right censoring, what we know is that in TI the company is still active and the lifetime of the company surely exceeds TI. This event can be just represented in probabilistic terms as STI, so the survival function computed in TI. So in the first case, Li is equal to Fti, that is to say Sti lambda Ti. In the second case, Li is just Sti. If we introduce the indicator di, which is equal to 1 if Ti is the actual time of default and 0 in case of right censoring, we can write our formula in just one line, and Li will be equal to lambda Ti to the power of di times Sti. Okay, just take the product over the n companies and you will have the likelihood function. Naturally, you can also define the log likelihood by taking the log of the likelihood function, and in that case the product will become the summation. What is important to notice here is that in the log likelihood we see the appearance of capital lambda ti, that is to say the cumulative hazard function. Why? The reason is simply due to the fact that we know that the survival function STI can be expressed as the exponential of minus capital lambda of Ti. This is the connection between the two functions. Okay, since I know that you want to test your knowledge, I have a little exercise for you. Assume that the default times of our companies, both censored and not censored, follow an exponential distribution. You see the density on your screen. Now, what I ask you to show is that the maximum likelihood estimator of the hazard rate lambda is nothing more than the ratio of the summation of all the indicators di of actual default censored observation and the sum of all the times ti. In the wake of what we have just seen in the simple exercise, we can make other parametric assumptions on each of the different elements we have considered so far: the hazard rate, the survival function, the CDF, the density. In any case, given the strong relationships among them, making an assumption on the CDF or the density has implications on the survival function and the hazard rate. So for example, if I assume that my random variable follows an exponential distribution, so the CDF is the CDF of an exponential, I automatically know the density, the survival function, and for example, for the hazard rate, I can show that it's a constant. So the exponential is just one of the possible models we can assume. In the first week, if you remember when we were sketching the different approaches to PD and LGD, we have very briefly considered other models like the log logistic and the Weibull model. Okay, the Weibull model is actually a very important model in survival analysis because it has very nice properties. It's a sort of basic benchmark model. As the name itself suggests, the Weibull model is a model in which we are assuming a Weibull distribution. For what concerns the hazard rate, you can see the functional form on your screen. Why is the Weibull model interesting? Because take the parameter p. If p is equal to 1, our Weibull model immediately reduces to the exponential model. If p is greater than 1, what we have is that risk increases over time, while if p is smaller than 1, risk decreases over time. On the course platform, you will find more details. Cox models represent one of the most important classes of models in survival analysis. It's a very broad family that was introduced in 1972 by Sir David Cox. Now, this is a very large class of models, and we cannot consider all the different types of models. We will start with the simplest case, that is to say, proportional hazard models. In a proportional hazard model, each counterparty I is characterized by an hazard function of the form that you can see on your screen. This representation tells us that there is a quantity lambda 0 of t, which we call baseline hazard rate, which describes the risk that all counterparties share, and it's associated to the fact that the covariates contained in the vector xi are all equal to 0. The element exponential of xi prime beta is conversely what we call a modifier, is an expression of the relative risk that can be higher or lower, and this modifier depends on the characteristics that we can read in xi. So in a proportional hazard model, what we are assuming is that the hazard function of each counterparty is a function of one or more covariates, and these covariates can influence, can change the risk of that counterparty. What we have seen is just the simplest example of proportional hazard model. Naturally, we can make it a little bit more general by assuming, for example, that the covariates contained in the vector x are time-varying, that is to say, their values change over time. We can also be fancier by defining the so-called general hazard rate model, in which the vector beta, the vector of the coefficients, is replaced with the vector beta of t, in which we are assuming that also the coefficients are time varying. Now, this is the situation, for example, when we assume that one of the covariates has an impact on the risk only in a given time window and nothing outside of this window, or when we think that the effect is increasing or decreasing over time. There are many possibilities, as you can imagine. Now, this is actually something quite useful when modeling the loss given default. Can you say why?